All right, friends, it is time to get rolling. Welcome to our second day of the 2022 Senior Seminar Series. We are joined by Harper today to give a talk about their research, and Graham Sazama is going to be introducing them.
Thanks, Rachel. So comes to us from Columbus, Ohio, and I have known. All right, we got applause for Columbus. All right. Let's see. I've known since Chem 116. There was a great cohort of several 116 students. We had office hour time, and we had very wide-ranging discussions, and sometimes even touched on chemistry stuff. That was a great pleasure of my teaching career, and then as M progressed through their chemistry degree, I don't exactly remember how. I think I just invited you into the lab at one point, probably because of seeing you in the organic lab and that you had the interest. So after that, kind of the rest is history. You inherited a project from a prior student that has lots of promise and lots of challenge to it. So we'll get to hear all about that. And then M will be taking a gap year and then applying for grad schools in some chemistry-related field in the near future. So can't wait to see where that ends up. So with that, the floor is yours, M.
Everyone in person hear me? Great. Thank you so much for that introduction, Graham. Hi, everyone. My name's Em. Today I'm going to be talking about the research that I've been working on with Graham, where I'm looking at accessing tetrasubstituted alkenes en route to the organic radical BAxPA, which is a lot of jargon, but I'm going to hopefully break it down for you all today, so in a digestible way. So first, I'd like to discuss what radicals are and how they work. Radicals can be defined as molecules that have an unpaired electron, and most people have usually heard of free radicals, and that is usually in a negative context. It is true that radicals are characteristically very reactive species, and that is due to the unpaired electron. Electrons typically want to be paired up, and that has to do with orbital filling of spin up and spin down orientations. But for this presentation, just remember that electrons like the buddy system, and when they're alone, they kind of freak out and want to get a buddy as soon as possible again, which is super fair. So that's why when we hear about free radicals, for instance, skin cream companies often market their products to prevent aging that can be caused by free radicals because they can cause issues in the body. And a pretty common example of a free radical is a hydroxide radical. So in the body, there are water molecules which can come into contact with various compounds that can cause the loss of a proton from that water molecule, which would lead to a hydroxide free radical with a lone electron on the oxygen. And because that lone electron wants to find a buddy, it'll go wherever it can find, which can damage your cells and DNA and result in negative health issues. However, this is not the kind of radical research that Graham and I have worked on. While there are radicals that can be harmful, there's ravaging your DNA. However, while there are radicals that can be harmful to humans, there are ways of stabilizing radical compounds and ways to make safe, stable radicals that can be useful for making new materials. So now that I can talk about how we could increase the stability of radicals. Well, there are two main ways of increasing the stability of a radical. One of those ways being stabilizing the overall molecule as a whole, and we can do that by increasing the number of double bonds that are present, which will lower the overall energy of the compound. So for instance, this is a radical that has quite a few double bonds, which allows for pi conjugation and delocalization of electrons, which does stabilize the radical. A second way of increasing the stability of a radical is to stabilize the location of that unpaired electron. And so with this compound, we can see that we have these bulky side components that are producing a sort of shield around the lone electron on that central carbon. And so those bulky components are able to protect that electron from reacting with other compounds. So for instance, I have here a space filling model, which is essentially just a three-dimensional version of the radical structure on the right. And so we can see here in 3 dimensions how the bulky components on the outside also twist and create this kind of bubble effect around the central carbons in a way that we can't even really definitively see looking at this where the little electron is located because it's so hidden within those bulky components. And so now that we've established that we can stabilize radicals, I have a few examples to show you of what other radicals that are stable look like. So one example is TEMPO, which is a nitroxide-based radical. So we have our unpaired electron on the oxygen there, and that is stabilized by the nitrogen and our methyl groups that kind of also bring a little bit of a barrier around that unpaired electron. Additionally, we have our phenylalanine radical, which is stable when we have our tert-butyl groups on the outside there, those little branches sticking out. And we also have, again, a lot of pi conjugation with those double bonds and our unpaired electron located at the very center. Additionally, we have BHT, and again, here we have the unpaired electron located on the oxygen, and again, our pi conjugation and our tert-butyl groups, which are really effective at blocking other compounds from coming in. And also TTM, which is a well-established radical structure. So here we have again, our unpaired electron located at the on the central carbon with our chlorinated benzyl groups sticking out, and we also have the three-dimensional twisting of those groups to create sort of a propeller-like shape to help protect in 3 dimensions. So with these examples of stable radicals, there have been proposed uses for various materials, one of those being OLEDs, which are organic light-emitting diodes. Also, we have OFETs, which are organic field effect transistors. And then we also have the potential for use of stable radicals in batteries and solar cells. And so with this, particularly with OLEDs, OFETs, and solar cells, the possibility of using radicals for these kind of technologies versus other methods is that we can actually increase the efficiency of these technologies. And with batteries in particular, stable radicals show promise for being good for the types of redox reactions that are happening within batteries. And having these organic stable radicals in particular can often cut down costs for these technologies. And for also with the use of radicals, we can also introduce the idea of flexible electronics, particularly with the use of radicals with OFETs. You can see in this image how you're able to kind of twist it a little bit. So we have, we're opening the doors for different kinds of flexible electronics as well with the use of radicals. But something we also need to consider in addition to the stability of the radical for these kinds of materials is its ability to emit light. I mean, particularly with OLEDs, the light emitting aspect is important, and so we want to see if we can make stable radicals that also are capable of luminescing and therefore emitting light. So what does that look like? There are some known stable luminescent radicals, and I'm going to bring back TTM because this is a known stable organic radical that also luminesces as is, and that has been well studied, and also a number of derivatives based on the structure have been made, such as pi BTM, where we're taking off a chlorine group on top there and putting a nitrogen into the ring, and that also shows luminescence. And another example is TTM2CZ, where we're actually just attaching these fluorine groups to the outside of the TTM structure. And so this has been an established way of synthesizing more stable organic luminescent radicals, but our group is particularly interested in seeing what other ways we can make stable organic luminescent radicals. And so our group has thought about using a known stable organic radical structure and then incorporating a chromophore, which is a luminescent component, and seeing if that incorporation can get an overall luminescent radical. And so for our particular research project, we are looking at BDPA as our framework for that radical structure. So BDPA is 1,3-bis-diphenyline 2-phenylallyl, also known as Kolsch's radical. It has been very well studied and is known to have a very stable carbon-based structure. And that has to do with the resonance that it has and the delocalization of electrons. I brought this picture up earlier to show how we can stabilize radicals. And particularly with BDPA, we're really interested in the steric bulk that is present in this molecule. So we have our 2 fluorine groups on each side, which are very effective in shielding that central lone electron. And so essentially we want to use this stable organic radical that does not luminesce as is and see if we can get it to luminesce by introducing a chromophore. So our chromophore of choice for my portion of this project is azaxanthone. And so I have 1 azaxanthone shown here. And we have chosen this as a chromophore because it shows fluorescent properties on its own. And also the structure of it is very like that of fluorine, which can provide that necessary steric bulk for the stability of the radical, because we want to get it to luminesce, but still maintain that stability. So in comparing BDPA as our basic structure, and then replacing that fluorine group with azaxanthone, we hope to get a target radical that we have named BAxPA based on that incorporation of azaxanthone. And because we are just replacing that group, we want to follow a sort of synthetic route that has been established for BDPA-based structures. And that kind of synthetic route begins with using a fluorinone and reacting that with a chlorobenzyl phosphonate compound. We are then able to get to a chlorinated tetrasubstituted alkene there on the left, and a brominated. If we react it with a brominated fluorine, we can then hopefully get to our BDPA compound. And so following this kind of route with our specific target radical, we aim to start with azaxanthone reacting with a chlorinated a chlorobenzyl phosphonate compound using the Horner-Wadsworth-Emmons reaction. We should be able to get to our also chlorinated tetrasubstituted alkene, react that with fluorine, and get to our final target radical of BAxPA. And so it seems simple when I break it down into these steps, but this is a long process. And so for my portion of this project, I have been focusing on getting to this tetrasubstituted alkene as my key synthon, particularly concerning the formation of the double bond that I've highlighted in red. And so I've said the words tetrasubstituted alkene a couple times now, so I should probably define what I mean by that. Well, a tetrasubstituted alkene is a bulky and crowded molecule. This is an example of a generic tetrasubstituted alkene, and basically breaking down those words, an alkene is something with a double bond. So we have our central double bond shown, and tetrasubstituted just means that we have 4 substitutions shown on the same double bond with our 3 benzyl groups and our chlorine. And so looking at our synthetic goals, we're looking at essentially going from a tetrasubstituted alkene with a closed 5-member ring to a closed 6-member ring when we introduce azaxanthone to get closer to making BAxPA. And so that is, tetrasubstituted alkenes are difficult to make because of us wanting the steric hindrance in order to maintain the stability of the radical, but also not having it too sterically hindered that it won't come together. Particularly going from again, the 5-membered ring to the 6-membered ring, we can remember that each of these carbons also has its own hydrogen poking out. And so with those, you can see going from the 5-membered ring to the 6-membered ring, we have a lot more clashing of the hydrogens from those phenyl groups. And so that is something that we need to consider as a challenge with this kind of synthesis. So with that, again, there's going from the synthesis of BDPA to the synthesis of BAxPA, we need to consider that we are changing the bond angles of these molecules. And so On BDPA, we can call that theta 5 because of the 5-membered ring, and this would be theta 6 because it's a 6-membered ring. And as we use the 6-membered ring, we can see that the bond angle is getting smaller, which again is offering us an additional challenge on top of already the challenging nature of making a tetrasubstituted alkene. However, I did mention earlier that while this is difficult, it is possible, and there's a reaction that is used for this kind of synthesis called the Horner-Wadsworth-Emmons reaction. So how does that work? If it's so difficult to fit these pieces together, how can we do so effectively? So the Horner-Wadsworth-Emmons reaction generically starts with our phosphonate ester compound using sodium hydride and our aldehyde. We can then bring our R group in and form this crucial double bond that is needed. I mean, with something something that is not sterically hindered seems a lot easier, but we also need to consider all the different components of our materials. So something that had been an issue for Kelly, who worked on this project before me, is that while she was able to progress with the synthesis, her yields and purity were not doing very well. And so we needed to take a step back and think about where we started before this Horner-Wadsworth-Emmons reaction and what starting materials we were using for that. And so initially, Kelly was using this diethyl phosphite with these loose ethyl groups on the outside, but that was proving to be difficult to work with because with this reaction, we are trying to target that central phosphorus atom. And so we considered if we could get those ethyl groups to kind of get out of the way so we can open up the accessibility of that central phosphorus, then we would have a more success in the synthesis. And so we proposed closing the ring and kind of handcuffing the phosphite together as such. And so that's where I came into this project and began with trying to synthesize the starting material, which I have called DDPO. So as this first synthetic step, I started with neopentyl glycol, reacted that with phosphorus trichloride, where I was able to make these chlorophosphonate ester compound, and then using ethanol, we could get to our DDPO, which again is just the pinned back version of our original starting material. So while this seems very simple, as I've broken it down into these 2 steps, it did not end up being this simple. And I spent most of 10 weeks trying to make this over and over again because I was having issues with the differences in purity of my products over time. So for instance, one of my trials where I was using triethylamine as a catalyst and using dichloroethane as my solvent, I got something that looked like this, kind of looks like an egg, which was pretty cool. But and then upon rotovapping, I was able to get this thick yellow goop. But based on the literature that I had seen, DDPO is supposed to be a white crystalline solid. So this is not technically what I was looking for. And so I was able to keep trying the synthesis with small alterations to the procedure. And so when I tried using triethylamine and a tetrahydrofuran as my solvent, I was able to get kind of an orangey colored substance with my leftover catalyst. And upon filtering that out, I got more of this like milky yellow compound, which again is still not a white crystalline solid. So for this trial, I used no catalyst and just used more solvent, going back to the dichloroethane. And that ended up giving me this kind of almost opaque white, still goop, but slightly better. And then upon drying it more on the Schlenk line, I was able to get these kind of flaky, crystal-y looking things, which seemed promising and a lot closer to white crystalline solid than the yellow goop. And so I was able to analyze these using phosphorus NMR. And phosphorus NMR is really cool because it's really quick and easy to just kind of check how things are going, because as a lot of us in this room know how proton NMR works, we're able to see what kinds of different protons or hydrogens are present in our sample. And so similarly, looking at a different frequency tuned to phosphorus atoms, we were able to see how many different kinds of phosphorus atoms are present. And so with this first spectrum, we can see 2 definitive peaks indicating 2 different phosphorus species present in my sample, with the most prominent one being indicative of DDPO. So I was having a successful synthesis, but I have some kind of other side product that is likely causing the issues with the texture and the color of that sample. For my second trial that I'm showing here, I had a lot more peaks going on, indicating that I was having a lot more issues with having side reactions and side products going on, but still having that prominent peak there indicative of DDPO. So still a successful synthesis, but some issues with purity. And then for this one, we have a really gorgeous phosphorus NMR showing just one super prominent peak, indicating that this was my most pure product that I was able to get over the summer, which was really exciting. So with these, again, I was having to make a lot of different alterations along the way in order to get from the first one to the last one there. So some of the things that I had to change with my synthesis were drying the glycol before the reaction. The glycol is very hydrophobic, and like as soon as I opened it up, it started sucking up water really quickly, and that could be part of the cause for some of the side reactions and other things going on in there. So I did work on drying that before using it. Additionally, to minimize water content in my reaction, I started to run it under nitrogen to also minimize any water in the atmosphere. So I have my little apparatus there, which also shows how I diluted my phosphorus trichloride reagent, because phosphorus trichloride is very reactive and was reacting very violently just as is. So when I diluted it, I was able to slow down the rate at which I was adding it and get a more steady mixture, which ended up working really well. And also I chilled my reaction flask down to -5 degrees using an ice bath and some rock salt, which also proved to be very useful for the addition of phosphorus trichloride. Additionally, I was not able to use an aqueous workup for this. I tried, but much like the glycol, the DDPO likes to be in water. So when I did an aqueous workup, and it didn't end up going into the organic layer and instead stayed in the water layer, which is not super helpful for what I was trying to do. So instead, I ended up having to use an azeotropic method of removing the water. So I was able to use toluene and this Dean Stark apparatus in order to remove the water, which actually was a pretty cool process. So despite having to make a lot of changes and having a lot of different purity levels of my product, I was successful in making DDPO, and so I was able to move on to the next synthetic step using what I had made. And so I was able to then combine my DDPO with benzaldehyde, use catalytic butyllithium in order to then form my hydroxybenzyl phosphonate compound. This worked out pretty well. Excitingly, again, with phosphorus NMR, I have 2 significant peaks here. So we can see that this taller peak is indicative of my hydroxybenzyl phosphonate compound, and this smaller peak actually ended up just being residual DDPO, which is a lot better than some other side products. So that was very exciting. And with that excitement, I moved forward with that and then making my chlorobenzyl phosphonate compound. So again, I used my hydroxybenzyl phosphonate from the previous step. Using thionyl chloride and pyridine, I was aiming to make this chlorobenzyl phosphonate compound, which ended up not working. So that was, so while I was only able to try this step once, so not like a huge bummer that it didn't work, because I still have faith that it can work, but there are definitely some changes that need to be made in order to more successfully synthesize this reagent before we can move on to the Horner-Wadsworth-Emmons reaction. So some of my hypotheses of what can be done for improving the synthetic step are purifying my hydroxybenzyl phosphonate. I was really excited, so I didn't really think about purifying it that much and just seeing if I could keep moving it forward after being stuck with DDPO for so long. So definitely I think purifying that could help, and also drying it out, because again, with the previous steps I was having issues with water. For my hydroxybenzyl phosphonate, I did quench it with water because of the butyllithium that I was using. And I did end up drying it afterwards, but I still feel like there definitely could be some residual water in there. And that could lead potentially to interactions with some of the reactants of this step, particularly with the thionyl chloride. I found that thionyl chloride, when it reacts with water, could produce hydrochloric acid, and also having my pyridine as a Lewis base in there could be reacting with that and producing some chloride salts as some side products that are not useful to me instead of making my desired product. So that could have also been an issue I was having. And then also, again, I only tried this step once, so I think as shown from my many, many trials of DDPO, I think I definitely would have to suggest just keep going at it and seeing what other alterations might need to be made for that synthesis. And then beyond that, the future work of this project, which is ready to be taken up by future students, which is super exciting, would definitely be to, once we can get the chlorobenzyl phosphonate compound, then we can move forward and hopefully get to our tetrasubstituted alkene, and then from there, hopefully fully synthesize BAxPA as a radical, which we could then confirm with electron paramagnetic resonance to make sure that we do have a radical present. Then we would want to see if we were successful in getting this compound to luminesce using the addition of our isoxanthone chromophore. And then if that was successful, the next steps would be to extend this method to see if we could attach any other potential chromophores to the BAxPA radical structure and widen the potential stable organic radicals that can luminesce, again, to apply to all those different kinds of materials and technologies. So I'd like to thank a few people. I'd like to thank Graham for having me in his lab and being a great research advisor. It's been a really great time. I'd like to thank Rachel for leading this class and doing a great job teaching us how to develop these presentations. I'd like to thank Stefan, who wasn't here, but he was also very helpful over the summer. I'd like to thank Deanna, who was my academic advisor and reminds me that I am a competent chemist, which is also, and Kelly for her past work and, positive thoughts with me taking it on after her. I'd like to thank my lab mates who went to San Diego with me to present this research at the ACS conference over spring break. Also, I'd like to thank DMART and the rest of the stockroom workers because I literally couldn't have done any of this without you. And thank you all for being here. I'm happy to take questions.
Okay, we are ready for your questions. In-person people, on Zoom people, you can type them in the chat or you can unmute yourself at a conveniently quiet moment. Yes, Ezra.
So on slide 23, you said that the synthesis didn't work. Do you have any idea why it didn't work and what product you made if you didn't make your desired product?
That's a great question. I don't know what I made. There are NMRs of this that I can no longer find. So I remember talking to Graham and being like, we didn't make it, got to try something else. And then I have no idea where those files went somehow. So I don't know what I made, but I do think, it could have been like I was talking about the water content and other things floating around in that crude from the last step. So I definitely think it just didn't get to where I wanted, but I have no idea what I actually made. So
File management is one of the least appreciated skills in research. Justin.
Yeah, I might have spaced it, but why is it useful to have the entire thing separate in S, right?
Because it is the stable radical structures that are very useful and have the potential for those material uses, but we also want the luminescent aspect, particularly for stuff like OLEDs that we need the compound to be able to absorb a photon's energy and emit that light effectively. Yeah.
Joe.
Yeah, my question on that is, so talk about
For sure, yeah. I mean, for stuff like OLEDs, it can be more efficient, or at least it has been proposed that it could be more efficient. I think that a lot of the stuff is pretty new. There's one example which is
that does beat the maximum possible internal quantum efficiency of an LED device. Okay, so when you look at the photophysics of a singlet normal molecule with all paired electrons, you get the maximum possible efficiency is 25%. When you look at radical emitters like these, you can envision up to 100% efficient. And there's one example with one of the luminescent ones that M showed that is 27%, so above the theoretical possible for a closed shell molecule. So there's lots of room to grow in that to get to 100%, but certainly better than 25.
Other questions for our speaker? Zoom people, this is your moment if you want to ask a question.
anyone.
Going once, going twice. All right, that's all for the questions then. Let's thank our speaker again. All right, so our next speaker is going to be Evelyn at 4 o'clock. So have a snack, hang out, and join us in 10.
Let me figure out how to. Thank you everyone for coming.